Dr. Foust, can you hear us?
Yes, I can hear you. Sorry, I moved the phone and accidentally just hung up. Can you hear me?
All right, proceed when you're ready. Yep, proceed when you're ready.
Okay. This is Thomas Foust. I'm the director of our Renewable Fuels Bioenergy program here at NREL. So I'm going to give you kind of a high-level overview about where biofuel stands right now in the overall context of fuels, chemicals, future directions. Okay, here we go. So anyway, the current situation of bioenergy is the overwhelming majority of gasoline sold in the United States, almost as high as 97%. So for all practical purposes, it's about 100%. Motor gasoline sold in the United States is E10, so 10% ethanol and 90% gasoline. That ethanol almost exclusively comes from corn ethanol. It shows right there on the slide, 13.3 billion gallons. That's produced, I'll show you the next slide where it's produced, predominantly in the Midwest, as you would expect from corn. Biodiesel, even though there's a relatively large number of biodiesel plants, 115 compared to 211 for the corn, they're much smaller capacity. So biodiesel production is essentially a tenth of what corn ethanol is, 1.3 billion gallons compared to 13.3 billion gallons. A lot of reasons for that. Biodiesel doesn't have as high of a blend margins and others. And then cellulosic ethanol, that's been a technology that's been under development here at NREL as well as other places. Really dates back to the late 1970s. There are 4 plants in the United States right now, 10 plants worldwide, 4 in the United States, that are producing cellulosic ethanol on a commercial basis. So here shows the distribution of biorefineries in the United States. As you can see, very centrally located, concentrated in the Corn Belt, Iowa, Illinois, Southwest Minnesota, etc. And then there's, like I said, most of those red dots are corn ethanol plants. There are 3 cellulosic ethanol plants on there, as well as one that's down in Florida. There's a cellulosic ethanol plant in Florida as well. Right now, biofuels production is relatively stable to stagnant, and I'll get into the reasons later about why that is the case. So here shows the history of cellulosic ethanol technology development. We started working on cellulosic ethanol, we being NREL, National Renewable Energy Laboratory, SERI at the time, in the late 70s. However, it was more of a fledgling research program. There was a lot of good technology developed, but there wasn't really a near-term path to market. There really wasn't a commercialization goal. So that all changed in the early 2000s. We set up a 10-year program, 12-year program, and then that was accentuated. As you can see, there's not a bar in 2006. And the reason that is under the then President Bush 2006 State of the Union. That's when he made the claim that cellulosic ethanol technology would be developed and commercially ready in 2012. So since that time period, we've benchmarked. We have pilot plants here at NREL, 1 ton a day. So we do technology. Well, we did. This is in the past now. Did technology demonstrations, and then based on economic models that we had, we would predict what the cost of a production, including 10% IRR, internal rate of return, would be. So this shows the progress made, quite significant, impressive progress. So in 2012, you see a cost of $2.15 a gallon. And at that price point, we could show cost parity with corn ethanol. Then corn prices were around $3 a bushel. and also cost parity with gasoline from crude oil. At that point in time, I think crude oil prices were around $75, $80 a barrel. Interestingly enough, both corn prices have come down since that point in time. Corn prices now are around $2.50 a bushel, so about a 20% reduction since they were in 2012. And crude oil prices are down significantly. They're roughly only two-thirds of what they were in 2012. Crude oil prices are about $45 to $50 a barrel in the last year. Most of the reduction in crude oil prices has been driven by fracking, horizontal drilling. So cellulosic ethanol is kind of in a bit of a precarious situation due to the low crude oil. And interestingly enough, corn prices in the United States do track oil prices. There's been a lot of studies to that effect. In every study, well, most of the studies have really concluded that there's so much fertilizer use, diesel use, fuel use in the production of corn that's why corn prices tend to track oil prices. So that's where we stand right now. And the work we're doing, and I'll cover in the rest of the presentation, is how to kind of break this logjam, how to move cellulosic ethanol and biofuels into a point where they're actually competitive with crude oil as low as $50 a barrel, and also new type of approaches where we can make better fuels from that actually advantage higher efficiency, lower polluting engines. So we were part of a UN study in 2013 that really looked at what the future of bioenergy should be, what should be the right role of bioenergy. And this UN study really determined that the best role of bioenergy worldwide in North America and the United States is it should be about 10 to 30% of the fuel supply. And if it's incorporated in a logical, systematic manner, it can have all sorts of positive impacts, resilience in food supply, decreased pollution, actually enhance agricultural production, and other. Also, switchgrass and other type of energy crops can actually be used to rehabilitate degraded lands. So that's the path that we're going forward, and I'll explain roughly where we are now. So like I mentioned, crude oil prices are very low. Nobody really has the ability, obviously, to predict the future. All sorts of events can happen that drive up crude oil prices, geopolitical events, etc., and those are quite unpredictable. But what is predictable is supply and demand. So crude oil demand has actually been decreasing in the United States since about 2005, especially gasoline. Demand is decreasing about a percentage point per year. That varies as a function of the economy and other factors. But if you look at it over the macro term, it's been decreasing about 0.8% per year, driven largely by vehicle efficiency and decreased miles driven in the United States, predominantly by the younger population. So what we're facing is a situation of where do we go with biofuels in this kind of price environment. So like I mentioned, we're looking at the best opportunity worldwide and in the United States, and it's not cropland, it's pasture land, which tends to be a generic term for land that has lower productivity. It tends to be semi-arid land, land not suitable for crops. And then also we're looking at energy crops on land that can be used in a dual cropping manner, where you grow, for instance, if you're in the Midwest, where you would grow a winter bioenergy crop that would be a nitrogen fixer to enhance the fertilizing value of that, decrease fertilizing use, and enhance food production and have no net negative effect whatsoever on food or land available for crop production. And then, like I was mentioning earlier, if you factor all those considerations into context, you can show a situation where biofuels can be used to produce 20 to 30% of the fuel supply. So in order to do that, one of the big challenges with the 4 cellulosic ethanol plants that exist right now is biomass is inherently a more complex substrate feedstock than corn or simple sugars. So even though great advances have been made in breaking down biomass to simple sugars and then fermenting to ethanol, as you can see by this flow chart on the slide here, it's quite a complicated process. So when you add up all those into, it's the analogy of death by 1,000 cuts type of analogy. None of the individual processes in of themselves is problematic or that costly. It's the entirety of their process is very capital intensive and quite complex. So the plants that exist right now are really struggling with availability, uptime, and those factors. So really we've been challenged where we see is dramatically reducing the complexity and hence the capital cost of producing fuels from biomass. So the next couple of charts I'm going to show you the approach that we're taking. So this in a simplified manner just shows that flow chart that I was showing you earlier in a more simplified schematic manner. So roughly the process is you pre-treat, condition the biomass, you do hydrolysis, which is an enzymatic process where you convert the biomass down into simple sugars. You clarify that, you do a co-fermentation, wastewater treatment, and then the lignin, which is a third of the biomass, is burned and produced to power. So through advanced biology and the research we're doing here at NREL, you can see how we're greatly simplifying this. So the first step is to combine the 2 steps of the hydrolysis, biomass hydrolysis and treatment. That has a fairly significant reduction on cost, almost 15%. And then even through better biology, again, there's the R&D on this is progressing and showing good progress. You can combine 4 steps into 1 step. So now you have a 6-step process that is 3 steps. And then ultimately through better utilization of the lignin, you can take a 6-step process down to 3 steps, of which 2 of these are proven technologies. So that's the research we're doing. And then this chart here dramatically shows the benefits of this. The base case was the first the first schematic that I showed you, which is essentially a representation of the existing commercial plants. As you can see at the scales below about 50 million gallons per year, the cost goes up dramatically. Put this in a payback time period. So about above 50 million gallons, you're into the 40, 60, 80-year time period, which is not a wise business venture to be investing in something with that kind of large payback. And it isn't until you get into the very large plants, 90, 100 million gallons per year, that you get a reasonable payback period of 20 years. In the advanced case, we're showing payback periods of 5 years, and you don't see the high tail like you do below 40 million gallons per year like you did in the base case. And there's numerous advantages to this. Radically shorten the payback period, improve the economics, dampen out the scale intensity, which reduces the capital cost. Hence, startup companies, smaller companies could be, you're talking about a overall plant cost of about $80, $100 million compared to the current plant cost of $400 to $500 million. So it opens up the business space for smaller companies, less capital intensive, less research intensive. So those are all good benefits, but probably one of the most important things is it does reduce the food versus fuel concern, so that's nice as well. The next couple things I wanted to show you was that one of the big advantages of biofuels is they can dramatically improve engine efficiency. This is a picture of a Tesla, not a biofuel car by any measure, but it really is setting the benchmark. A Tesla or any kind of electric car could have a fuel cost of about 3 cents a mile, whereas regular conventional cars running on gasoline is considerably higher than that. So with biofuels, we can enhance fuel efficiency. This shows the fuel efficiency standards. So we're working on that. This shows the advantages for using the oxygenate, both in spark ignition gasoline engines as well as compression ignition diesel engines. And then finally, one of the big advantages of biomass is if you look at crude oil refining, it's the 85-15% rule. 85% of the volume of the crude oil goes to fuels, but 15% goes to chemicals, but that's 85% of the value. So in order to make biofuels competitive, you have to use make chemicals that are higher value chemicals. And this is a real inherent advantage of biomass because the oxygenated functionality in biomass can make better products, better chemicals, and really enable a whole new performance-based products like rain-resistant jackets to better tires that have better temperature range, so you wouldn't have to be changing out winter, summer tires, all sorts of potential advantages, more flexible snowboards, skis, etc. So this is an area that we're really advancing on. So that's really what we see the future is better fuels for higher efficiency engines, lower emitting engines, as well as better chemicals. So with that, I'll end my presentation, and I think then next we're going into Peter Sikowski that's going to give you a specific example